All right. Well, I myself feel very pleased because it was raining yesterday. After 600 days of drought in Kaohsiung, finally we have a big rain last night. Okay, feel a little bit of easy today. Okay, let's go back to what we're trying to say today. So driving big loads. Why we need to talk about this? Because your chip is very small. Okay, your chip is very small. Then you have something like a nuts in the middle. Then, after your calculation or whatever you want to do in the chip, you want to send your signal out to drive the pad. And these are called pads. And the pads, they use bond wire to connect to the PCB board. PCB board. This is bond wire. This is pad. This is bond wire. Okay, this is a small guy. So the pads, bond wire, the PCB, they are all gigantic load to this little one. So we need help. We need to help the little guy to send out a signal so that the PCB board or the or the scope can fully understand what the operation is. So because this is a small signal, very small current, and this is a huge load. So it's impossible. Just like how the hell you can use a ping pong ball to drive a big wall. It's impossible. So you got to find something else to help. Then we need a buffer. This is called a buffer over there. Okay, larger load might be driven. So including the off chip, the clock wire, a long wires on chip. So sizing on the driver transistor only pushes back the problem. Driver now presents large capacitor earlier stage. So what does that mean? That means if you simply use one single driver, it won't work. For example, now this driver, okay, according to your knowledge, the driver can be implemented by 2 inverters in cascade in a serial order. But the thing is, this is big, this is small, okay, on both sides. So you want to drive big, these 2 inverters must become big, relatively big, almost the same size. Then these 2, at least this one, this inverter will become the load, the C load of your small driver. So you simply don't solve the problem. You just leave the problem, okay, push the problem back a little bit, keep pushing back. So apparently, a single inverter or a single buffer cannot solve this problem. And instead, we got to use another design by using the design that we talked about before. Okay, this is a way we do to drive big load. Let's assume this is a giant, big one, and we have a small, teeny tiny dwarf on the left-hand side. We don't use a single inverter or buffer to drive it. We use a series of N-stage inverters, okay, and their size are increased step by step. They equally distribute the load over these stages. For example, the first one, okay, is W over N. And in the next stage that it drives, the width is increased by alpha times. Okay, that means, okay, I only deal with alpha times of load. And then increase a little bit. Then in the next stage, which is driven by the second stage, we again increase the size by alpha times. Okay, alpha times. Then to the end, the capacitance okay, generated by the final stage will be somehow equalized to the load that you want to drive. Okay, it could be somewhere equal or about the alpha times. Then the entire series of buffers or inverters, okay, is functional to drive this big load. And this kind of design, we have a special name for that. It is called a taper buffer. Taper buffer. The basic rule for you guys to follow, that you will see something like this. Okay, this is your core circuit. Okay, you use a series of inverters. And the size, the first one is a unigain. For example, 2 to 1. 2W versus 1W. There's a very standard inverter. 2 times of width for the PMOS, and the unit width for the MOS pull down transistor. Then in the next stage, we increase by 3, maybe 4 times. Remember the ratio that we developed before, okay, for the driver design. Okay, according to the logic efforts, then in the next stage, we either times 3, maybe 4, it's up to you. Okay, maybe 4. For example, if you decide to times 3, it will become 6W versus 3W. The next one will be and the last one will be equivalently or almost equivalent to the C load over here. Okay, this is called the taper buffer. And you can increase by 4 times because we have a fan-out 4 rule before, in our analysis of logic efforts. So this is how we do it, okay? So please do not directly, okay, use your signal to drive the pad. It's impossible. It's not readable for any external instruments because the current here is simply too small, and the pad, the bound wire, and the PCB board, and the access port, they are all big loads. It's impossible to drive them. So you got seek help from the taper buffer, all right? And you can increase the size by 3 times in each stage. All right, this is the cascaded driver circuit. It's called a taper buffer. So we use a chain of inverters. Each stage has a transistor, okay, larger than previous stage, all right? And the minimum total delay, we can do this, okay? If you know the load divided by, okay, your core circuits, okay, the capacitance, you take a natural log, you will find out how many stages you need, okay? Let's assume, for example, over here, you have usually, for the C load that we use, minima is 20 picoF. Okay, 20 picoF, that's the minimum. That's including the pad, the bound wires, and PCB, about 20. But for certain applications, if you want to use the oscilloscope, it could be as high as 60 picofarad. 60 picofarad. Then the driver of, no, I'm sorry, the signal source in your core circuits, if let's assume it's 1 picoF. Okay, so how many stages you need? You take the 20 over 1, take the natural log. You got your number. This is n, the number of stages. You got that? Is that clear? It's very easy. This is a load that you assume. Basically, 20 picofarad is required. But in order to ensure that your circuit will function just fine, even if you use the scope, you got to add up to 60. So you take the natural log of these two ratios. Okay, it depends on how big your internal circuit is. Then you can have the number of stages and stages. Okay, then every stage you either increase by 3 times, maybe 4 times, it's up to you. Okay, because the optimal number is somewhere in between. So that solves the problem. Okay, so driver size expansion tapered by size ratio alpha. You just increase it. Don't forget this one in the final stage of your chip design. Otherwise, even though your core circuit functions just fine, but you will never see it from outside because your signal simply cannot pass the pads and the bound wire. You don't see anything. It's totally blank. You see a lot of noise, that's all. Is that clear? So this is the last step that you need to take, okay, to finish your chip design. Okay? So this is something I did not conclude the last time. Right now, after the static logic, we're going to talk about something really fancy. It's called a dynamic logic circuits. Okay, I'm not sure any team who's still in this course wants to take this dynamic logic. But I'm telling you, dynamic logic is quite welcome in the past 3 decades because a lot of professors, they can publish paper. They publish papers. They make many announcements that they discover new circuit design, logic, this kind of thing. Okay, so dynamic logic is interesting, but it has its own limitation, and it also has its features and the benefits. Okay, let's go to see what dynamic circuit logic is. So in this talk, we're going to cover the basic dynamic logic and single rail dynamic logic, dual rail, and a clocked, 4 types. Okay, basically, it covers everything about dynamic logic. Okay, I want to erase these dates. So, does everybody copy this down? Okay, make sure you understand what we're going to do in the rest of this semester. Let me repeat again. We're going to have a final exam on June 12th. Then you're going to submit your chip design, okay, before June 16th. And then the TAs and I will finish all the grading and submit your final score to June 21st by the deadline of set by the university. Okay, so let me refresh your memory about the static logic. So we have a static logic, and now we have dynamic. Okay, what is the difference of this one? Static logic, basically, it has a P block. Okay, then it has an N block. P transistors, N transistors. Okay, and this is ground. And the output is generated between these 2 blocks. And we have the same input, okay, coming into these 2 blocks, so that the P block and N block, one of them will be on. Okay, if the P block is on, then we have a high. Okay, if the N block is on, then we have a low. That's it. This is called a static. Basically, no clock. It has nothing to do with the clock. Okay? And for the dynamic logic, it's slightly different. I'll tell you the final answer. Dynamic logic, okay, because as we said before, the P blocks, of the static logic occupies too much area, it's slow, and it's power consuming, so no one likes it. So we like to take them away as many as possible. So we like to keep the M block. But instead of the multiple P transistors, we only keep one. Then in the bottom of the N block, we have another N transistor. This one is called the foot. It's like your foot over here, okay? Then these two transistors, they are driven by a single clock source. So this one design is with clock. So right now we have a very major difference on the table. Okay, so how to make a differentiation between these two logics? Static has no clock, and dynamic logic is driven by clock. All right, so just look at it, you find out that the size, the area of the dynamic will be much smaller because only one P transistor is needed. Okay, and all the other P transistors are kicked away. But however, since the clock is required by the dynamic logic, you can imagine that this kind of a circuit, it might be very power consuming, particularly when the clock frequency is high. Because you remember that we talk about the power dissipation is proportional to what? The frequency, the C, which is the area, and the V square, voltage square. So apparently, when you increase the frequency of the clock, okay, the dynamic logic will cause a lot of power. But however, it is fast. Okay, so you can see that this will be smaller, okay, faster, but high power. Okay, so it has its limitation, as I said. So some of the applications, some of the scenarios that you can use a dynamic logic, okay, in any case that when the speed is a top priority, clock-driven dynamic logic is a top choice, okay? So this is a dynamic logic. Basically, you just got to remember these two pictures, okay? This is the cornerstone of these two different designs. Okay, so dynamic logic, the information is stored in the charge form. All right, the information is kept by a charge. And it is simply, you can consider it as a sample and hold and dynamic logic. We're going to go to the detailed operations of these special circuits. Okay, so this figure is much more prettier. Okay, this is what? Static logic, right? We have a P block, we have an N block, right? This is over here. And this is dynamic logic, it's over here. This is one, look like this one, right? Okay, and something weird in the middle. Okay, this is something that we talked about before. Instead of using the clock, and we don't like to use the too many P transistors, we have a pseudo NMOS. That the load P MOS is always grounded, so we have a constant current source from the power supply. Then the logic value is defined by the on and off of the N block. However, the voltage here will be decided by the ratio of these two resistors. So we call this as a ratio design. And based on our discussion in previous chapter, that the best, or I should say the optimal ratio of these two blocks, P MOS N block is 1 versus 4. That's what we talk about. So you got to remember these numbers, okay? So remember these figures, static, pseudo NMOS, and now we are going to dynamic logic. Okay? And this is a ratio that students like most. Because why? Because we like to know the size. Then we don't have to think. We just copy it down and draw the circuits in the software. So static logic, okay, it's quite easy, 2 versus 1, because the mobility of PMOS is slower. So the width is twice as big of the NMOS. And this is a pseudo NMOS. You take away the 3, now you will see that this is 1 versus 2, right? But this is the NMOS. The mobility is double of the PMOS. So technically speaking, the driving power of these two parts is 1 versus 4. So it is a correct number, you got to remember. If you only use a pseudo NMOS, 1 versus 4, okay? And for the dynamic logic, it's quite easy. Remember this number, 1 versus 1. That's it. The driving capability is that, all right? 1 versus 1. And then, because the mobility of the N transistor is much bigger, so in fact it's 1 versus 2. Okay, in terms of the driving or current sinking capability, it's 1 versus 2. So please remember these numbers. Okay, you're going to use it, okay, in the entire chapter. Okay. Now the next thing is this figure. What the hell does this mean? I'm going to erase this. All right. Dynamic logic is a charm. Okay. Many of my previous students, they publish papers and design their chip using some different types of dynamic logics. It works just fine. Okay, what the hell does this mean? Now, please pay attention to this one, all right? I'm going to draw it. Okay, now please pay attention to what I'm going to draw over here. So this is the clock, and it's called a phi over here. That's fine. Okay, so the clock is a periodical signal all the way, okay, in time. This is time, right? And what happened is that, okay, this is y. Okay. So now what happened when clock is low? So when clock is low, when it's zero, this is 0. What's going to happen? Okay, when this is 0, over here, so this one will be turned on. Right? And what happened here? This is 0, right? This one is blocked. So I don't care what A is. No matter A is high or low or something else. As long as this one is disabled, there is no path. So nothing will be discharged. Right? So in this, this kind of scenario, this is why. I don't know what that is. I don't care. Okay? When the clock is driven low, then we definitely should have what? To have, when this is low, we guarantee Y will go too high. Is that clear? So this one is called the pre-charge. So when phi equal to 0, we are going to pre-charge it. Pre-charge y to high. No matter what A is, I don't care. Okay? So there's nothing over here. Okay, pre-charge it. Now the next thing is clock eventually will be pulled down. Okay, will be pulled high. It's low and now it's become high. Y equal to high. What's going to happen here? Because here we always have a load. Okay? So in the previous pre-charge phase, we have stored some information here using the form of charge over here. So then, when the clock turns high, okay, it's blocked with nothing over here. No one will be coming to help to charge the Y. So whatever left here become a problem. If A right now is high, and when clock is high, then we have a path here. If A is high, then we have a path to discharge whatever just happened. Okay, so the Y will go to 0. So we have a 1, we got 0. Is that clear? Okay? Very easy. However, if A is 0, then we have no charge. We have no path. Then Y will remain the same as before. So when phi goes too high, then we have two possibilities. What is that? Is one will become 0. The other one will remain high. So in this phase, we call evaluate. Over there, evaluate. So, and then clock turns low again, we're going to pre-charge it again. And then when clock is turned high, then we are going to check A to see what the logic value is. All right? So we do this way all the way down. Okay, continuously and repeat periodically. So the basic rule is that according to the high and the low of the clock, we are going to have two phases, pre-charge and evaluate. Is that clear? And this arc, this arc with the arrowhead shows that, okay, the the consequence or the order of the event. Okay, so the pre-charge will cause this event, and the evaluate when the clock is driven low, then we are going to have a pre-charge again. So you got to get used to this symbol. The arrow, the arc with the arrowhead stands for the order of event. Order events. The arc. Order of event. Okay, you gotta go this way. When this happen, and this will be happen. If nothing happened, there is nothing happen here. Okay, there's an order for that. Okay, they are not happen on the same timeline. Is that clear? Okay, you gotta understand this, then we can move on to the to a little bit more complicated circuits. Okay, you gotta remember this one. We have two phases in dynamic logic: pre-charge and evaluate. Okay, Now this is prettier. Okay, this is unblock. Okay, and pre-charge phase. Pre-charge phase, that means when this is low, this is blocked, that one is turned on, so the F will be charged. Okay, it's nothing to do with what happened over here. And when the clock is full high, that one is off, this one is on. Then what happened here means something. Okay, if it's a pass, we're going to have a low. If it's not, we're going to keep the state as before, or keep the state as before. Okay, and the circuit here could be so complicated. It depends on, okay, what kind of logic you use. Basically, the design of the unblock follow whatever we talked about before. Okay, based on the logic equation, Boolean equation, that's what you need. Is that clear? So in this case, you're going to find out, okay, what is the function in that unblock? You will see that one pass is W and V. The second pass is X and Y. Okay, and the last one is X and Z. So the F, that's a Boolean equation over there. Okay, W and V, the first term, and the second pass, X and Y, and the last one is X and Z. That's it. And this is a Boolean equation in that schematic. Okay, this is dynamic logic. So whatever you can write in a Boolean equation, you just reverse it and use the unblock over there to realize it. Okay, that's it. Easy peasy. All right, of course, someone else will come up with a totally different idea. Okay, if we can do the unblock, why don't we do the P block? So the P block is a symmetric design of that one. So for the P block design, we are going to have a P block. Okay, and this is a foot. Okay, and this is where the output is. Where the output is. Okay, that's a P block. But the thing is, sorry, the figure is wrong. Okay, if this is the case, the clock is slightly different. Okay, here we gotta have pre-discharge, not pre-charge, pre-discharge. That means when clock is high, okay, we pre-discharge everything. Okay, no matter what that is, I don't care. Okay, and this one will be blocked. We pre-charge everything. And then when clock is low, we do evaluate. Okay, when clock is low, and there is no path to discharge it, it's blocked, then this one is on. So we are going to determine whether the state of the output is 0 or it is high. Okay, so it's totally opposite to the previous unblock dynamic logic. It's P block, but this kind of block rarely used because what? Look at this gigantic stuff. Okay, all the P transistors are there. They're too big and slow and very power consuming. Okay, there is only one scenario in this textbook, in this course, that P block will be used. That is a so-called complementary dynamic logic, and we'll go to see that, okay? So for the unblock, it's a normal and widely used solution, but for the P block based dynamic logic, it is only used for the NP domino or so-called complementary dynamic logic, that's all. Okay, used as auxiliary circuits, not major circuits. So this is just an example used in the textbook, that's all. All right, now let's go to see the size, because students love size. Let's ask information. Remember that we say that the dynamic logic is 1 versus 1, okay? Remember that? If you forgot it, let's go back to check it out. See that? I told you to remember this one, this basic scenario, 1 versus 1. Okay, don't forget that. Based on this rule, so when we have a series of unblocked, we simply enlarge the size, because we need a 1 versus 1, right? So if this is a circuit you want to design, this is what? This is a NAND logic. Right now we have 2 N transistors in the N block, and we need another foot switch. So a total of 3 stacked NMOS transistors. Then we have no choice but to increase the width by 3 times, so that we can fit the rule. We meet the rule of 1 versus 1. That's the way it is. And this is this is the circuit of 2 stacked NMOS. We got to increase the size by 2. Okay? Now you understand the rule, right? Please follow it. Please follow it if you do the dynamic logic design. Okay, and it's where I told this some of the students designed using dynamic logic. But recently, I'm going to have Indian students graduated with his degree, and his major research is using certain dynamic logic to implement a carry lookup header. I told him to follow the rule that he simply does not like it. It's weird. It's nice to have your own idea, but you got to have a series to prove it or back it up. You can prove the professor is wrong. I always say this, okay? Young man like you got to have the guts to challenge the authority, but you got to have the substantial evidence or substantial theory to back it up. I told my graduate students, what does research mean? Research means that research starts when students tells the professor that you are wrong. Otherwise, it's not a research. You just do whatever the professor say. It is not research. Let me repeat. You're going to be the graduate student very soon, right? Okay, what does research mean? Research starts when the students tells the professor that you are wrong. That means you have a guts to challenge the authority. You give a guts. You have guts to come up with a brilliant new idea, and that's research. Otherwise, you just follow whatever the professor says. You got nothing. You have nothing but just a tool to implement his or her idea. That's all. It's quite pathetic. Okay, but unfortunately, students don't listen to me. Yeah, that's fine. All right. Anyway, so another question often asked by students is that, why do we need that foot over there? What if we don't have the foot? Okay, whether the dynamic logic can work? The answer is not. I'm telling you why. Okay, let's assume there is no foot over here. Nothing. Okay? There is nothing over here. And then you have a simple clock over there to drive the circuits. So you have a clock coming over here to drive the clock. So what's going to happen? Okay, what's going to happen? This is a clock, and this is A. Okay, the arrival time of A does not have anything to do with the clock, right? Okay, the signal of A can be changed any time. So right now, if you want to use this as an inverter, let's check it out. Okay, so when clock is 0, then we expect it will have a pre-charge. Okay, so that Y will become 1. But suddenly, when A equal to 1, what's going to happen? What's going to happen? Okay, all the current, all the charge delivered by the power supply, okay, might not go to the load. They might be directly drained when A is high, so that you don't have the pre-charge anymore. You see my point? Okay, when there is no foot, you don't have the guarantee that the CL or Y can be pre-charged, because there's a risk that A could be high. Then we have a discharge path. Then Y will be pulled down to 0. That is dead. It's a dead logic, not dynamic logic. Is that clear? So you gotta have the foot. Without the foot, the logic function cannot be maintained. Okay? So use a series evaluation transistor to prevent fight. That's why. When the A is suddenly turned on, excuse me, or the inputs here suddenly make the F to pass, then we have a problem, because it's a pass, this is a pass. Then we don't know what the value Y is. You don't know that. Okay, it could be 0, it could be somewhere in the middle, but I guarantee it will not be 1. Okay? So right now we're going to talk about something bad about the dynamic logic. Okay, there are a lot of problems with dynamic logic. As I said at the beginning of this course, that IC design means to find something, okay, to do the trade-off. Okay, you give something, you get something, you give away or take away. So here, because the dynamic logic is faster, it's smaller, but it has a lot of boundary issues. And this is one of them. It's called the discharge hazard. Okay, what is that? It's a little bit complicated. Please follow what I say over here. Okay, right now you see that we have one dynamic logic followed by another one. Okay, this is one, this is one. And they are driven by the same clock. Technically speaking, if they are both, if they are static logic, okay, you got no problem. You got no problem, okay, for example. That's a logic gate, whatever that is. Okay, if this is static logic, you have no problem. Whatever happened here will be generated and propagated to the next stage and all the way down to the right. Nothing happened. Okay, everything is just fine. So if you implement the circuits by static logic, you never pay attention to this kind of hazard. You just simply integrate it, that's fine. But if you're using dynamic logic, that means we have a symbol like this one, dynamic logic. Then we have an issue. What is the issue? Here, G. Okay, just like a G over here. G over here. What could be the problem? Okay, let me tell you one. So, according to the definition of dynamic logic, when clock is low, that means every output of a dynamic logic gate must be poor charge, poor high. Is that right? So this is the first stage. So we expect the G is poor high because this one is blocked. And then, excuse me, and when the clock is low, they are all blocked, and this one shall be poor high. Correct, right? No problem. Okay? So there's something weird over here. This is a poor high. So what happened here? This transistor is on. Is that clear? This transistor is on. So this is the logic over here. So the voltage here, there, technically speaking, it should be as high as the power supply, VDD. But since this one is accidentally turned on by the previous stage, so we find out there is a charge sharing problem over here. That's like this one. The voltage of F will be pulled down a little bit because this one is excuse me, is coming down over here. It's called the sharing, charge sharing. So this partially discharged hazards. Okay, that is, if you directly couple the output of a dynamic logic to the input of another one, you gotta have the risk like this one. Okay, the F is supposed to be pre-charged, pre-charged high, but when it's do the evaluation, even though in the evaluation, okay, it's it's on, okay, it is high, but it will be discharged a little bit. And if it drops too much, then the zero will become unknown. The one will become unknown. That we call this is erroneous state. It is caused by the partially discharge. So we got to do something about it. Otherwise, from time to time, we might have a risk that the output could be wrong. Okay, so this is discharge hazards. Okay, so how do we get rid of these hazards? Hazards means something could be the problem, could be in danger. Okay, the first solution is the most popular one. It's called a domino logic. Okay, it's nothing to do with the pizza. Domino pizza, one of the worst pizza in the world. I don't know, you guys like it or not. Okay, have you ever tried a domino pizza in Taiwan? Domino pizza? You never eat a pizza? Oh, come on, man. Okay, how about Pizza Hut? Pizza Hut is much better, right? It's more expensive, but it's worthy. Okay, the Domino, I'm sorry. Okay, they're recording. I might be sued by Domino Pizza, really bad. I'm gonna ask a TA to edit it, okay? That's terrible. But Domino, I gotta say something good about Domino. Okay, the fried chicken seems to be very delicious. I don't know. But as an old man, I always tell myself and my family to stay away from the junk food. Well, I'm telling you the same thing, okay? For those stuff, okay, provided by fast food chain stores, okay, it's better for you guys to stay away from those things. I know they taste delicious. I know they look like fancy, but the thing is, they're trash, okay? They're trash. Come on, a lot of powders with grease and oil, okay? That's something that you don't need. You need vitamins. You need protein, okay? You need good oil, not bad oil, okay, to keep yourself healthy. Is that right? Okay, TAs are here. Let's take a break, and let me get some coffee. If you have something to discuss with your TA, I think it's a good time for you to do that. I will come back 20 minutes. You only have a discussion with them.